All right, well, welcome everyone. We're very pleased to welcome you to the Harry R. Hughes Center for Agro-Ecology seminar series. Just a little background about the seminar before we get started. We're a 501c3 nonprofit. We're affiliated with the University of Maryland College of Agriculture and Natural Resources. And our mission really is to promote environmentally sound and economically viable agriculture and forestry as Maryland's preferred land use. And we do that through research, outreach, and collaboration. And I want to mention that when we say agriculture in Maryland, we define it broadly to include aquaculture, and we fund research to some extent, and the presentation today is going to be one of those projects that we funded a few years ago, and is just wrapping up now. So we're very excited to hear about this. We, as a nonprofit, we have a board which includes prominent people in the agriculture and environmental space in Maryland, including at the state level, we have a senator and a member from the House of Delegates that are on our board that help guide our work, focused primarily on looking at what issues Maryland has that need to be solved. One of our main roles is actually to help spur research that will address roadblocks that the state has to the development of prosperous and environmentally sound working lands in the state. So again, we're looking at economic viability along with environmental issues that may arise. And so we have an extensive process where we work with influential people throughout the state, including our legislative members and members at our departments of ag, natural resources, environment, et cetera, to determine what the main issues are that need to be addressed, and we try to spur research in those areas. Again, I'm really pleased to share one of the projects that came out of that process, and introduce Dr. Slava Lyubchich, who is a research professor at the University of Maryland Center for Environmental Science. He's located at the Chesapeake Biological Laboratory in Solomons, Maryland. And he had a project very highly anticipated, and that generated a lot of interest among our board when he proposed this research. And he is going to talk to us about advanced machine learning for factors that will improve oyster hatchery production. And I would urge everyone, please hold your questions until the end, and we will take questions and discussion following the seminar. And also, I urge you to follow up and check out information on our website, because we have, in addition to Dr. Lyubchich's research, we have funded several areas in aquaculture, several projects in aquaculture over the past 3 or 4 years, and I'm sure there's other research that you would be interested in. So with that, Dr. Lyubchich, thanks again, and over to you.
Hi, thank you very much for the introduction. I hope you can see the slides okay.
Looks good. Thank you.
Thank you. So I'm glad to present the results of our research, which was sponsored by the Hughes Center. And the topic which was advertised, can machine learning help grow baby oysters? And for which one I found such a nice picture. But as I was preparing the talk, and I'm a statistician, so I was very heavily drifted towards describing all the methods that we applied to tackle this problem. I would rename the talk a little bit more as what machine learning finds about growing baby oysters. And here's another background picture, like from a Matrix movie, where we are looking through lots of data, and we're looking for patterns in the data. So this is what I'm glad to present today to this audience. First of all, I would like to mention collaborators who have helped tremendously through this project. Matt Gray and Greg Silsby from Horn Point Laboratory from the same University of Maryland Center for Environmental Science as myself. Srishti Vishwakarma has started helping us throughout the project with machine learning with neural networks. She was a former student at AMSIS. And Stefan Alexander is a hatchery manager who has provided us with data and lots of the feedback on the use of the data and how can we interpret it. Funders of this project, I should include Chesapeake Bay Trust, which supported the beginning of data collection and sort of the data mining for this project as well. So the challenge of oyster aquaculture is has several facets in that. First of all, oysters are ecologically, economically important. They are used for restoration activities. They are used to support families who rely on aquaculture farming. Who grow oysters on the leases, and United States is importing a lot of seafood, so developing aquaculture industry is one of the priorities right now. The hatchery production faces challenges due to inconsistent yields, and not only at the example hatchery, which we are considering here, but also across hatcheries in the United States. Like low yields or inconsistent yields have tremendous economic impacts because a lot of time is lost during the growing season of oysters. And of course, lots of funds can be lost because of the low yields or low output of the hatchery when they do not produce enough oysters. So we want to understand and predict this variability, and hopefully we can help in that. So to investigate the variability, we want to identify the key influencing factors, and you will see that we are looking at a lot of different factors. Our specific goal was to identify indicators of high and low yields. I would say particularly low yields, which are also termed crashes in the hatchery, when almost no oysters are produced after several days of incubating them in the tanks. And we wanted to provide actionable insights such that we would use variables or predictors in our analysis, which would be known to the hatchery at least a few days ahead of time, so they could foresee what's going on and possibly cut cost by basically dumping the tanks ahead of time when the low crash is predicted with high confidence. Sorry, when the crash of production is predicted. So we wanted to provide the opportunity for the hatchery to enhance the cost effectiveness of their operations. There are some pictures I found from the hatchery. These are showing spawning, filling tanks with eggs, and tanks in the hatchery, and we are mostly using the data for this process about eggs being in the hatchery, but also then the small oysters are placed in a setting pier where they are settled on substrate, like such as the old oyster shells, and they are distributed across the bay for different projects such as restoration and aquaculture. The hatchery itself is this red dot, the Horn Point hatchery, and the blue dots show the other data sites which we use to collect information about weather and water quality. So this is our list of most of the data sets we have used. About the hatchery itself, we had records where the broodstock was collected, conditioning which was used in the hatchery, information from the spawning stage, and information about the larval culture. From the buoy side, Goose's Reef buoy, from the weather stations next to the bridge here in Cambridge and the Cambridge Airport, we collected information on water quality, such as chlorophyll concentration, salinity, turbidity, water temperature, and also air conditions or atmospheric conditions such as air temperature, wind direction, speed, and so on. We also tried to fill in some missing data, which were missing, frankly, mostly because of the instrument failure in those collection sites when the sensors for weather were not functioning well. So we tried to fill in the information with like regression techniques to have more data available for analysis. We also used remote sensing products, normalized difference vegetation index in the Choptank River watershed, which served as an indicator of vegetation health and was used to approximate the agricultural practices in the area, or land use practices. We hypothesized that, for example, application of fertilizers can affect the water quality and increase the greenness of the crop nearby. So that's why NDVI would be considered important. We were able also to have chlorophyll estimated using the remote sensing product. So we had some of the redundancy in the data sets because we also had chlorophyll concentration from the buoy readings. In the processing stage for these data sets, we also created lagged variables. Lagged means delayed in time. So we could analyze, for example, the effect of water quality a few days before the production started. We had dates when the tanks were filled with water for the initial production. So we could or lag that times to incorporate the additional information. We even aggregate information for winter conditions, just in case there were some pathogens or some other water quality parameters that could affect oyster production and water quality in general. So with all these variables, there were more than 100 variables in total because of all different lags considered additionally to the ones listed here. With all those variables, we wanted to forecast hatchery yields. Hatchery yield was formally derived or calculated as the percent of eyed oyster larvae produced in the tanks from all the eggs added to tank. Since I already have presented some of the findings from this project, I received some feedback that even eggs added to tank could be an uncertain number. because it's really hard to count them, but we have the more like we are dealing with the most accurate data we have, and I should say that the Horn Point hatchery is one of the hatcheries which collects and maintains data well compared to some others that I have had a chance to see before. So what we have is a large data set with many variables, and we were not sure exactly what variables are the most influential, and we wanted to use machine learning techniques to process these huge data sets and find patterns. And we used two general approaches from machine learning called random forest and neural network. They're quite different. The common between them is that they are looking for patterns in the data in a data-driven way, such that compared to physics, where the relationship is known, here we are looking for the relationship between the data. Random forest builds so-called decision trees or regression trees, where the data set is split based on predictors. We choose the predictor each time automatically such that it splits data in a better way, so the splits are more distinct one from another. And then information from many such trees is aggregated in voting or in averaging, and then the average output is generated. Neural network is acting very differently. In the input, we have all our predictors. In the output, we have the known yields. And through a series of so-called layers, hidden layers, 1, 2, and could be many more, we are modifying the inputs such that they would match the outputs. Again, the training is happening in a data-driven way, so we are not dictating the forms of the relationships, but let the neural network find the patterns on its own. And the value of this, of connecting input to output in this way, is that the hidden layers eventually will help us to forecast the output given the input. So if we learn well what's happening in between, then we can use inputs for some new case and forecast the output. We also applied some algorithms for selecting predictors in the random forest framework. We used the Baruta algorithm. It is an algorithm for random forest processing, where we would shuffle copies of predictor, combine with the original predictors, and then see what if the importance of some predictors is actually below than the shuffled copies. It means that they are not really important, because shuffled are not important by definition, because they're like bogus predictors. So we would test that, and we'll be able to weed out predictors which were not important for forecasting yields. How we verified that important versus not was during so-called tenfold cross-validation, when we took our training set, or the whole data set that we collected, and we split it into 10 sections or folds. And at each iteration of the algorithm, we used 9 folds to train the methods, and used the left out data, the testing fold, to test. So in the testing fold, we used the predictors to forecast the yields, and then compared the forecasted yields with the actual observed yields, and we would get the error estimate. And we would get 10 error estimates after tenfold cross-validation. So when we ran all of that, these were some of our results for verifying or validating the predictive modeling capabilities. This is a root mean squared error measured for different methods. The first 5 plots here show the errors for random forest techniques, whether we applied all predictors, Baruta selected, recursive selection, or another technique called interaction forest, which would supposedly select pairs or triplets of predictors which can act simultaneously on yields. And the thick horizontal bars here denote medians from tenfolds, and the boxes are from the 25th to 75th percentile. So we see that random forest is considerably outperforming neural network in general. But we still kept neural network in our further analysis for further comparisons, because again, it's a very different approach and it can lead to different patterns that we could identify. So we ended up using Baruta recursive algorithm to without predictors in random forest and used all predictors in neural network. That's our methods of choice. We were able to rank predictors' importance. Here we see that week, when the production starts, is one of the most important predictors in how successful it will be. Also, winter NDVI was ranked highly by random forest as one of the top predictors. Then we have a sudden like a threshold or drop in the importance of predictors, and then we have fecundity, the number of eggs produced by spawning oysters, turbidity measured at Goose's Reef, and other water quality variables. We were also able to look at so-called partial dependence plots, or look at what exactly happens with change of week, or what exact impact we would expect if we are, for example, starting the production in week number 20. The points here represent the actual effects that random forest would predict, that our yields, hatchery yields, would increase by, say, from 1 to 2 percentage points. And if we start at week 30 or later, then the average yields would be lower by, say, 4 percentage points. And similarly for other factors, we see that, for example, higher salinity helps to grow more oysters, and so on. So we could look at individual factors, and we could also look at individual predictions. Here we took, for example, 3 cases of crashes when the actual yield was very low, close to 0. And we tried to apply random forest and neural networks to explain them. First of all, we see that the average yield in the whole data set was about, the average predicted yield by random forest was 9. I should mention that the actual was 10, so it was very close to be correct. But for this particular case, we observed that the production started at week 34. So this fact already decreased the expected yield by 2.9 percentage point. Also, NDVI was of this value 0.27, so this also had a negative impact on the expected yield, and so on. At the end, the forecasted yield was 1.4, so very close to being a crash. For the same case, neural network was not as accurate, I would say, for this one, because the forecasted yield was 9, but we also see some of the variability in explanations here. We also looked at the positive examples, of course. So here notice that weeks are often at the top, so the later weeks explain a decrease in production quality. And interestingly here, weeks are also at the top, but not always as in the crashes. So what we see here is that combined effect of other features is mostly prominent. We also see that lower turbidity values help to obtain higher yields. For example, these yields were of about 25%, 22, and again 25. So these were higher yields from the data set. And again, we see some of the deviations with the neural network. And I should say that here we need to readjust the numbers, because for neural network training, all predictors were scaled from 0 to 1. So here the numbers were rounded to zeros for display. So what we can see, or what we can use these models for, is to act on specific cases, because many of these variables you see are well known in advance, such as water quality and week of the year, of course, and even the winter conditions. So we can recommend some management actions, such as temperature control and water filtrations. We can further run economic analysis to see if we can recommend discharging the brood, so the hatchery does not continue with the production, to save money. We would also, of course, like more data for training our models. In this project, we had to filter out a lot of data when the broods were mixed together, and we couldn't track easily what conditions they were in the hatchery, because for example, when some part of the brood was dead already, so somebody would decide to put them together to save the tank space. We hoped to further improve the hatchery's ability to manage their production and reduce the variability of yields, or at least improve the predictability of yields. Again, we are looking forward to continue working on this project and help hatchery growers and help the restoration activities with this analysis. Thank you very much for your attention.
Thank you, Dr. Lyubchich. Before I open it to questions, I think I need to say that this is being recorded. Is that correct, Josh?
That is correct. And I just made it so that participants can unmute themselves and ask a question. So if you have a question, either pop it in the chat or you can raise your hand and we'll call on you. You can unmute yourself and ask your question.
Great, thank you. So I will get it started. I have a question, and this is because I don't know much, if anything, about neural networks or machine learning. But in one of your figures, it showed how certain parameters that you were measuring, there was a point where there was a very sharp drop off rather than what I would expect in other data I've seen where it would be sort of a slower change at some point. Is that an artifact of this kind of technique, or is that, I mean, how would you explain that? So for example, when you were looking at week, it seemed like there was like a really sharp drop off at a certain week.
Right. So some of these plots we think show threshold effects. And it could be an artifact of the technique, like you said, because random forest finds a threshold to split the data compared to some techniques like regression techniques where we find a function that can smoothly approximate the data sets. So we should acknowledge that, yes, in the description of the results that the random forest method fits a piecewise function or piecewise description of the data. However, I also think that the thresholds can be useful for managers when we can say that after this value, this is the critical threshold after which, for example, the yields is going to deteriorate.
Thank you. Yeah, that's interesting.
So we got a couple of questions in the chat. Number one, do the week numbers correspond to calendar years starting on January 1st? And if so, would that make the 30th week the end of July?
Yes, the week number corresponds to that.
Great. And then another question, was the salinity used in the model incoming salinity or the culture salinity after augmentation?
I think we had at least two salinities. We had average conditioning salinity in hatchery, and we also had Goose's Reef measured salinity at this point. So this salinity is labeled with GR. So like here, so this comes from Goose's Reef buoy.
Excellent. And then I don't see any other questions in the chat. If you do, please go ahead and pop them in there, or if not, raise your hand and unmute yourself.
I have another question on the data that went into the model. So you mentioned at one point that some of the data was lagged. Can you talk a little bit more about, so it seems like some of these parameters that were measured were probably what happened maybe a week or 2 weeks or even more in the past might have been influential in what the outcome was. And how does machine learning account for that or adjust for that or take it into the model?
Certainly. Yes, we tried to incorporate logged variables to represent better different factors that can affect the oyster growth. For example, some of the physical conditions about water quality could also affect the development of pathogens or microorganisms which would affect oysters, but we didn't have exactly the data on that. That's why we wanted to approximate it with the physical conditions, with lags. So some of this could be incorporated in that effect for microbes and so on. And for lagged variables, we included them explicitly with certain lags of number of days, or in general, like winter was average over the winter months.
Well, Kate, I don't. Here's another question just came up. What would a possible effect of winter NDVI on yield or crashes?
That's a great question. We hypothesized that winter NDVI would mean, like, higher winter NDVI would mean a warmer winter, when some of the pathogens can overwinter. However, again, we had some feedback from other researchers as I was presenting. It could be also significant of cover crops implemented. So it's a little bit like double meaning for in winter DVI here. It could be implementation of cover crops, such as that a good agricultural practice, or implementation of fertilizers, and winter being generally warm, such that the greenery persists.
Great. Well, I don't see any other questions or hands raised. So, Kate, do you have any last words?
Well, we just got another question, I
Oh,
think.
yes, we do. What do you assess the effect of cross-correlation contributions to weak?
We haven't cross-correlated weeks with other variables, but we can take a look at that. We can hypothesize that, again, some other feedback I received, that weak effect can be representative of also feed quality, the food that is given to oysters, and unfortunately we don't have data on that. So that is like something which we would like to research more if we have more data for the analysis. I also see the question on the time frame for the experiment. That was about, if I remember correctly, about 10 years of data we had from the hatchery, ending around 2020 or 22.
So this kind of goes to your last comment about you'd like to have more information on feed, what the feed source is, like what looking at the data you had access to, what types of parameters do you think were missing, or do you think might have been informative if you had access to them?
From what I heard about the feed quality was the like the nutrient content of food, like protein content, which, as far as I understand correctly, reduces throughout the growing season. Growing season starts from spring to the fall each year.
So thank you. Let's just give a little bit of minute more to see if anyone else has any questions. while we wait for that, Josh, would you pop our the website maybe in the chat so people could check and see and stay in tune with future opportunities to learn more information about this project or other projects that we funded. And then there is an additional question, and that is, was the data collected year-round or just during the production season in the summer months?
The data were collected for each brood that was not mixed, and because we knew the date when the brood started, so we could backtrace and collect the environmental data for that period as well.
One of the co-PIs here just put in the chat too that the production season is from April to September. So
Thanks,
that's
Matt.
from Matthew Gray, who's I believe also on this project. So thank you. Well, in the absence of any other questions, I'd just like to thank everyone for connecting and the thoughtful questions. Again, I urge you to stay in touch with the Hughes Center, this project, as well as other projects that we have on aquaculture. We had several funded over the past, as I said, over the past 4 years or so. But most especially, I want to thank Dr. Lyubchich for presenting this information and looking at the importance of these parameters. This has been a huge issue that we've heard about at the Hughes Center for many years, and we're really hoping that this will help give some clarity and move the production and this particular aquaculture system along and improve it in our state. And before I end, I do want to recognize that there's one more question that kind of can wrap us up here, I think, and it's that the question is, are you looking to replicate the methodology in other regions?
I currently don't have an exact project in mind, but yes, that would be very interesting to do, and because hatcheries across the United States experience rapid crashes, and it will be great to identify common patterns across them.
And then again, Matthew Gray put in that other hatchery networks in Europe seek to replicate this approach as well. Well, again, thank you very much, Dr. Lyubchich.
Thank
really
you.
appreciate all your work and your presentation to the group.
Thanks for having me.